Okay, I think we can now get started. So today we'll talk about linear programming. And a corresponding method, simplex method. So actually today's content is very important, so I'm very glad to see that you have come. So okay, so for linear programming, I think for this concept, you guys might have already learned it in senior high school. So just to consider this example, say you have x plus y is less than or equal to 1, and negative x plus y is also less than or equal to 1. Then what is the mean value of x plus 2y? Have you guys encountered this kind of problem in senior high school? Yes. Okay. So when we were in senior high school, these kinds of problems it's not hard to be solved. So we can just so we sketch a coordinate system and we see that x plus y is less than or equal to 1. So we draw this line. Take a seat, please. Okay, so this is the first inequality, and the shaded area is the feasible region. And for the second one, it's y less than or equal to x plus 1. So it is something like this, and this is the feasible region. And we want to know that what is the minimum value of x plus 2y. So this is equivalent to say you let b equals to x plus 2y. So that's to say y is negative 1/2 times negative x plus b. Am I correct? Yeah, I think I'm correct. Okay, so that's to say you plot some line that has slope negative 1/2, and you want to minimize it. So you can do, or maximize it, whatever. So you can just look at this feasible region and to see. So you see that this is the feasible region. So we can just move this line by changing its intersection with the y-axis until you find the minimum value or maximum value. So we see that in this example, the minimum value is negative infinity, right? Because you can just decrease the intersect to any value. Okay, so this is a very easy example that you may encounter in senior high school. But the problems that we mainly encounter in this course, I think many problems in this course that you encounter can be transformed to linear programming, but of course not in the senior high school style, because you need to look at a more general case in which you have much more dimensions than those you encounter in senior high school. So generally, a linear programming, LP, linear programming can be written as the form is like you want to minimize or maximize z equals to C1x1 plus until Cn(xn). This is your objective. You want to minimize or maximize this linear equation, this linear function, and it should subject to some constraints. The constraints is like a11x1 to a1n(xn). This is less than or equal to or greater than or equal to b1. So you have suppose you have these linear constraints. So this is actually am1x1 and until amn(xn). This is less than or equal to or greater than or equal to bm. And also, you can say that x1 up to xn is greater than or equal to 0. So I think, so how many constraints do we have? We have m plus n constraints, right? These are m constraints and these are n constraints. These may look a little bit weird, but I will explain later. So you see that any linear programming, you can just write in this form, but this is not standardized enough. So in order to come up with some method to solve the general linear programming method, we need to standardize it. So the standard form of linear programming, standard form of LP, you can just write in this way. So you also want to minimize or maximize something. And Z is C1x1 and until Cn(xn). This does not change, but here is what you do. You make it to be A11x1 So you see what happened. In a standard form, it is not inequality constraints, it is equality constraints. And you can suppose you have m constraints. I want to say that this is Bn, and also with x1 up to xn greater than or equal to 0. So this is the standard form, and so you see the difference between the left and the right. What's the difference? The difference there's no. So you see that there's no difference with respect to the objective function. The objective function is always a linear function with respect to our x, and x is the variable that we want to determine its value, so that to minimize or maximize our objective function. But the main difference is that, so you see, these constraints are different. On the left-hand side, it might be inequality, but on the right-hand side, we always transform to equality. Can anybody tell me how we can achieve this? Transform some inequality to an equality. How can we achieve this? Okay, that's a very good point. So that's to say, you add some additional variable, right? So this additional variable is called slack variable. So, let me just give you an example. So suppose you have x1 plus 2x2 less than or equal to 6. Then what you need to do to transform this inequality to an equality is that you add a slack variable plus say s1. This is equal to 6, and you want s1 to be non-negative. This is the trick that you can use to transform this inequality constraint to an equality constraints. All right. So let me just list the point when you want to standardize a linear programming. So the first one is need to convert the inequality to equality. And this can be done by adding slack variables. And you should always keep in mind that the slack variable should be non-negative. So that's to say, if you have something, say x1 plus x2, this is greater than or equal to say 5. And what you need to do is to say you set it to be x1 plus x2 minus s1, and this is equal to 5. So in this way, you always make s1 to be non-negative. All right, so this is the first point. And now let's see the second point. The second point, I can just write it down here. So you want so second point is that we want to make unrestricted variable to be non-negative variable. So what does this tell? What does this mean? So suppose you have some xi. In your problem setting, xi can just be any real number. Then here comes the question: how can you transform xi to be non-negative variables? So let's say this xi can be some people's, some person's fortune, and it can be positive or negative. If it is negative, he's in debt, right? So how can you transform this xi, which can be any real number, to be a non-negative? Can anybody tell me? Oh, please.
Absolute value.
Absolute value. Think about it again. So this xi can be any value. So let me give you some hint. You transform it into the subtraction of something. So that's to say my goal is to transform it into non-negative variable. So that's to say, here you have one variable. When you transform to non-negative, you can, how about making it to be two variables? How can you achieve this? Okay, so I just tell the trick. So suppose you have some xi, which can be any value that you like the example that I have given. It can be either positive or negative. So what you do is to let xi, this is equal to xi prime minus xi double prime. Please be very please note that this is not first order derivative. This is not second order derivative. These are just two additional variables. So in this way, you also let xi prime and xi double prime to be non-negative. So in this way, you can just explain any real number by two non-negative variables, right? Okay. This is the second point. And the third point is transform the maximization to minimization. Oh, sorry, I made a mistake when I wrote the standard form. So in the standard form, I wrote minimize or maximize. So please correct it. In the most standard form, it should be minimization rather than maximization. So you need to transform the maximization to minimization problem. This is widely used in any kinds of optimization. People just talk about how to find the global minimum, local minimum. So we're always searching for the minimum. But in some problems, it may ask you to maximize something. So an easy way to transform from maximization to minimization is just to take the negative. Let's say this is your function, and you may need to find this maximum. Then what you do is just to take the negative. So it becomes like this. And then the maximum point now becomes the minimum point. This is very easy. Okay, so the last point is that non-negativity on right-hand side of constraints. Actually, I will explain this later when we talk about simplex method. But just to keep in mind that, so you see that we have some constraints. Let's say, say x1 plus x2 equals something, and we always make the right-hand side of the constraint to be non-negative. So that's to say, if you have x1 plus x2, this is equal to -5. So what you do is to transform it to be negative x1 minus x2. This is equal to 5. So I will explain why do we need to transform the right-hand side to be non-negative when we talk about simplex method. So as I have written, so you see that the minimization, oh, I already erased it, so let me write it again. So you want to minimize the z, this is c1 x1 up to cn xn, and the constraints is something like a11 x1, a1n xn is equal to b1, am1 x1, amn xn, this is bn, and you have x1 up to xn to be non-negative. So actually this, have you guys all learned linear algebra? Okay. So actually we can transform this into, we want to minimize the z equals c transform times x such that, so you see that from a11 to amn, actually this is matrix A times x. This is equal to B. And what you have here is that, so your C and X should be in Rn. They are n-dimensional vectors. And your A, you can write it to be M, N, R. Okay, so if you guys go to take the matrix analysis course, that's EN.553.463, this course. And the Professor Daniel Fishkind will tell you that. So when you want to explain a matrix which is of dimension m by n, and it is a real matrix, so you can just write it this way. And this R means it is on the vector field. The vector field is real. But in that course, he will talk a lot about complex matrix. So it is written in this way. But never mind. In this course, we will never talk about anything related to complex. Okay, so this is in B. It is Rn. So this is the standard form. This is the standard form of our linear programming. So what can we say about this? So you see that in many problems, actually our constraints are inequalities. But when we transform them to be equalities, we need to add slack variables, right? So that's to say, we see that the matrix A is of dimension m by n. Can anybody tell me any relationship between m and n? M should be less than n, greater than n in most cases. Let's just say mn, who is larger? N should be larger, right? Yeah. So let's say originally you just have x1 plus x2. You want to minimize this, and you have constraints. Let's say 2x1 plus 3x2. This is less than or equal to something, and say x1 minus x2. This is less than or equal to something. And then after adding slack variables, the number of equalities now is 2. That's to say m is 2. However, what is n? You add one slack variable for the first inequality, and you add another slack variable in the second inequality. So that's to say n is equal to 4, right? If you want to transform this into a standard form. So that's to say A is a 2 by 4 matrix. I will not erase this part. So what can we say? We can say that A, it has a rank n, and also n is greater than or equal to n. Then, what can we say about any feasible x? Okay, so I tell you a concept. We say so I first tell you a definition. An x such that ax equals to b and x being non-negative is a feasible solution. Now that A has rank n, A is and it has dimension n by n, and n is greater than or equal to n. What can you say about feasible solution? Is it unique? Can you tell me? Let's just say A has shape like this, and it times some, and your x should look like this. This is A, this is x, and on the right hand side, this is B. A has rank n, n is greater than or equal to n. Can we say that the feasible solution is not unique? Okay, I just tell you. Okay. So in this case, A has rank n, and n is greater than or equal to n. So this tells us that feasible solution is not unique. This is a very important thing. So if you don't remember why, just review your notes in linear algebra. So the feasible solution is not unique. Then that's to say we need to consider the feasible region. Okay, so I tell you another concept, feasible region. A feasible region in optimization we just denote it by S. And this S is such that X and X is a feasible solution. That's to say, you want to optimize something, you want to minimize your objective function. Then you need to search for the optimal X. Then what is the domain of X that you want to search for it? And this domain is the feasible region. So we have seen that AX equals to B with X being positive, X being non-negative. Because of the dimension, because of the rank of A and A's dimension, we know that the feasible solution is not unique. So that's to say, that's to say our feasible region, this set S has more than one solution, right? So our objective is to find the best S, to find the best X in this feasible region. This is our objective. So then let's look at this feasible region S. What can we say about S? So we can say that S is convex. This is very important because actually in linear programming and also the simplex method, what we are doing is a convex optimization. And I can say that in the optimization problems, convex optimization is the most fundamental because let's review what is a convex function. So convex function looks like this. It is like a bowl shape. So if you have, can anybody tell me what is the definition of a convex function? You see that this is a convex function. What is the definition of a convex function? Okay. First, you should remember that it is a bowl shape. Actually, when I was in undergrad, my optimization professor told me that, oh, a convex function should be a bowl shaped, but his English was not good. He's a Chinese guy. And it sounded like bullshit. So everybody just burst out laughing. So remember that it is bullshit. Okay, so a convex function means that for any x1, x2 in the domain of f alpha x1 plus 1 minus alpha x2, this is less than or equal to alpha f x1 plus 1 minus alpha f x2. And this is for any alpha in 0 to 1. So in this graph, you can say that, okay, so suppose this is x1 and this is x2. And x1, x2 can be chosen, can be any value in the domain of f. And then what is on the left hand side? F alpha x1 plus 1 minus alpha x2. This is just to say you connect x1 and x2. And if you want to, because you know that alpha is between 0 and 1. So alpha x1 plus 1 minus alpha x2 means that there should be, it is some point between x1 and x2. And then this is the left hand side. This is f, this point is f alpha x1 plus 1 minus alpha x2. And what is on the right hand side? Alpha fx1 plus 1 minus alpha fx2. That's to say, you connect x1, fx1 and fx2. And this is the right hand side. That's to say, the function is always below this line segment, right? So this is the definition of a convex function. And now we are looking at a set. We say that a set is convex. So you actually, the definition of a convex set is very similar to a convex function. So I read the definition. S is a convex set, means that for any x1, x2 in S, and any alpha between 0 and 1, you do a convex combination of x1 and x2. This is also in S. So think about it. Convex set, let's say in the Cartesian plane, okay? This is a pentagon, and it is convex, right? You learned this in secondary school. Then if you look at this definition, for any x1 and x2 in S, so suppose this is x1, this is x2. And for any alpha between 0 and 1, alpha x1 plus 1 minus alpha x2, that's to say, any point between x1 and x2 is also in S. So this is the definition of a convex set. A convex set looks like this. But I remember in my secondary school, my teacher just told me that, oh, that's to say, from any side of this polytope, you can just, okay, then the whole region is on the same side of this, right? But this definition is not rigorous enough. This is the rigorous definition of a convex set. Okay. Did I tell you why it is important to say that S is convex? Oh yeah, I said that. That's to say, when you are doing a linear programming, you are actually doing a convex optimization. So doing a convex optimization, you see that your feasible region is always is also convex. All right. What else? Okay, let me introduce another very important thing, and then I need to introduce one more concept, the vertex of a convex set. So let's say you also have this pentagon. This is a vertex. This is also a vertex, right? So a vertex, this is also named as extreme point. So what property does a vertex have? So a vertex, I can tell you that a vertex means that X in S is a vertex if for any distinct x1 and x2 in S, and for any alpha between 0 and 1, x cannot be explained by alpha x1 plus 1 minus alpha x2. So think about this. So suppose this is a convex set, and this is your, from the shape you see that this x is a vertex, right? Can you find any two distinct points in this pentagon such that you do a convex combination and you can get x? Can you do that? No? Okay. So that's to say this is a vertex. And you might be confused. Why do I need to talk about a vertex? Okay, so let us just understand it from a graphical perspective. You see that I have already said that our feasible region, that's all the x that satisfy the constraint. Our feasible region is convex. Let's say this is our feasible region. And you want to optimize, you want to minimize some linear function. This is what you want to optimize. You want to adjust its intersection with the y-axis until you find the minimum point. And I also introduced the concept of vertex to you, the vertex. So the truth is that the optimal point should always exist in those vertex. Can anybody think of why? Let's just say you want to adjust the intersection of this line with the y-axis. Regardless of whether you want to find a maximum or minimum, as long as your search space, or say your feasible region, is a convex set, then the optimal value must occur in the vertex of it. So you can just prove easily by contradiction that. So suppose your optimal value is not at a vertex, and then you can always push this. You can always push this line towards a vertex, and you can obtain a smaller value of it. So keep in mind that for linear programming, your optimal value must exist in the vertex, and this is how the simplex method do. I can tell you that for simplex method, actually it is searching along these vertices until you find a minimum point. So that's why people use simplex method, and that's also the reason why simplex method is so good. Because, so suppose this is your feasible region, then you have infinite number of feasible solutions, right? However, we know that it is convex, and our objective function is linear. That's to say the optimal value must occur in vertices. And for this, you see that this is a pentagon. For the number of vertices is finite, right? So in this way, you have transformed some optimization problem that has infinite number of feasible solutions to a finite number of feasible solutions. And you can just search among these finite number of solutions and check who is the best. So this is the core idea of simplex method. Okay, and let's just do a brief review of the linear algebra, and I will start talking about simplex method. So you see that the vertex is the definition is there, and then we can say a theorem. Our X in S is a vertex if and only if the column vectors AK of A corresponding to positive components of X are linearly independent. Okay, so I give you 30 seconds to look at this theorem and think about what the hell it is talking about. So an X in S in the feasible region is a vertex if and only if the column vectors of A that corresponds to the positive components of X. And always keep in mind that X should be non-negative. As to say the non-zero components of X, those corresponding column vectors are linearly independent. Why? Because if you just take this out, those column vectors of A that corresponds to the positive components of X, you can just write it to be, say, A prime. These times X prime, these are the linearly independent, these are the columns that corresponds to the positive components of X. A prime times X prime, these are the non-zero entries of X. We want this to be equal to B. And we know that the columns of A prime are linearly independent. Then can we say that this X prime is unique? It is unique, right? And then you cannot find, say, X1, X2, which also satisfy this equality. And in this way, X is definitely not be able to be explained by the by a combination of X1 and X2, right? By a convex, X cannot be explained by a convex combination of X1 and X2. So keep in mind about this theorem. So, oh, I should not erase this. I should erase this. So have you already copied this theorem? Okay. So keep in mind that what does a vertex tell us, and how can we relate it to linear algebra? Linear independency. This is very important. Okay, so I want to explain what does simplex do. To understand what does simplex do is much more important than memorize how to do it. Actually, how to execute simplex method, this is not hard. You can just search on Google and they can tell you that, oh, in the first step you do what, in the second step you do what. But it is more important for you to understand why it makes sense. I remember that in my undergrad, I heard the term simplex algorithm. I just thought that, oh, simplex algorithm, then it must be simple. However, when I learned the procedure of simplex algorithm, I saw that, oh, damn, this is not simple at all. So what does a simplex algorithm do? As I said before, in a linear programming problem, your search space is convex, and the optimal value must occur in a vertex, right? So this, let's say this is our search space, or say our feasible region. So 1, 2, 3, 4, 5, 6. These guys are what we want to examine. We want to examine who is the best, just among these 6 guys. So a simplex method does is that, let's just start here. We start here, and then we go along some direction that improves the objective function the most. That's to say, suppose you can go to an adjacent vertex, or you can go to another adjacent vertex. However, if you go to this guy, it can help you to decrease the value of the objective function by 10. And if you go to this guy, it can reduce by 20. Then which direction do you go? You go along this direction because it improves your objective function the most. And suppose finally you come here at this point. Suppose when you come here and you check that wherever you go, the value of your objective function will increase. Then you can stop. And this is the optimal solution. Can anybody tell me why? Why can I stop if I find some vertex such that for any adjacent vertex in this feasible region, the value of the objective function should increase, and then I can stop, and I'm pretty sure that this is the global optimal solution. Why? This
area that contains till y,
mm-hmm.
the infinite space, like that point is rest. So.
But how about say your region is closed? How about your feasible region is closed?
Yes,
like
I
this?
mean, all other points are contained.
Okay, so actually you can just tell me one word. The one word is convexity. Because as I said, this region is this is a convex optimization. That's to say, let's say you search in this area, and you have already found a point such that for any neighborhood points, this guy's neighborhood points are all better than, are all worse than him. Then you should be able to reach, then you are already at the optimal point. This is because of convexity. And actually, this idea is widely used in any optimization problem. So generally, when you talk about optimization, what do we do? Suppose this is the feasible region, and this is our objective function. What we do is just to find a direction that can help us to reduce the value of your objective function, and you go along that direction. This is just to say, I let you to close your eyes, and you walk on a mountain, and your objective is to find the lowest point among these mountains. That's to say, every time you walk in a direction that help you to reduce your height, or say you go along the steepest direction. So in optimization, there's some method called steepest descent method. And actually, in the simplex algorithm, you have more than one direction to go. You pick the best one. Who is the best one? The one that reduces the objective function's value the most. So from this perspective, it is the steepest descent method. You go along the steepest direction. Okay, so then we can talk about the simplex algorithm. Oh, by the way, so yesterday when I held my office hour, a student came and asked me about using MATLAB to solve linear programming. I think this is in your homework problem, right? So this is very easy. Actually, I can even say that in this problem, MATLAB is just a calculator rather than a programming language. You can just search on Google using MATLAB to do linear programming. And then you can search for a document, and you can just follow the document. You need to input your objective function and your constraints. The constraints, you can just input your function, your matrix A and the vector B. And then you call some function like linear programming, and then it can give you the optimal solution. Very easy, just several lines of code is enough. to. We just have five minutes left. Okay, so let's say we have an example. You want to minimize minus y1, minus y2, minus y3, such that y1 plus 5y2 plus 4y3 plus y4. This is equal to 1. And 3y1 plus 2y2 plus 6y3 plus, say, y5. And please note that y4, y5, these are slack variables. This is 1. And 5y1 plus 4y2 plus 2y3 plus y6. This is 1. And 2y1 plus 6y2 plus 3y3 plus y7. This is 1. And we also want y1 to y7 to be greater than or equal to 0. So according to what I have already explained for the simplex algorithm, this is what we do. So we construct this panel. The panel is like, so first we look at those constraints. We write the coefficients down. Say 1, so the first constraint is 1, 5, 4, 1. These are the coefficients. And for y5, 6, 7, these are zeros. And accordingly, the second one is 3, 2, 6, 0, 1, 0, 0. 5, 4, 2, 0, 0, 1, 0. 2, 6, 3, 0, 0, 0, 1. And the last row is the coefficient for the objective function. 0, 0, 0, 0. And here we write the vector b on the right hand side. And in this place, this is the value of our objective function. And this is what we do in every round. First, we want to choose the most negative coefficient on this row. And then let's say we pick this one. Why? Because you want to go the steepest descent direction, right? So you pick the most negative one. And then look at this and this. So here you need to memorize something. So you see that, let's say this is column 1. This is let's say column 2. We just number it to be column 2. Then what you need to do is to choose the smallest positive ratio for column 2 over column 1. Let's say the ratio 1 over 1 is 1. 1 over 3 is 1 over 3, 1 over 5, and 1 over 2. Then the smallest one is this. That's to say you pick this row. This row corresponds to this variable. That's to say you want to, then you do elementary row operation like what you did in linear algebra. As to say you want to make this guy to be a basic variable and this to be a non-basic variable. And in this way, I think we have run out of time. So let's do it in this way. We end our class now, and later today, I will just make a video about the way to do the simplex algorithm by this example. And I will also upload that video on YouTube and provide a link to Dr. Costello so that you can see how to execute the simplex method afterwards. Okay, is that okay? All right, so let's just end here.